Hello everyone. Welcome to our continuation of our discussion in Module 8, Part 1 with the topics carboxylic acid and esters. We're then discussing about the structures, derivatives, naming, etc. of carboxylic acids. We'll now proceed with one of the derivatives of carboxylic acids, which are esters. Let's take a look back at our outline for Module 8, Part 1, specifically focusing on esters. For esters, we will be discussing about its structures and different examples. We'll also be discussing a chemical reaction involved in esters, which is esterification. And then we'll proceed with the naming or the nomenclature of esters. Let's start with the discussion of the structure and give some examples about esters. So what is an ester? An ester is a carboxylic acid derivative wherein the OH portion or the hydroxyl portion of the carboxyl group is replaced with an OR group. The ester functional group is COOR, and its structure looks like this. As you can see, if we are to compare it with carboxylic acid, which is C double bonded to O with an OH bonded to it, okay, we can see that the hydroxyl group is replaced with an OR group, wherein R is the rest of the group. So it can be an alkyl, acyl, or an aromatic group. Here are the other forms in which we can recognize ester. COOR, again, is the functional group, and this is also the linear form in which we can recognize the ester functional group. It can also be represented by CO2R. Next, let's look at the simplest ester we can find, in which it has two carbon atoms. Kindly take note that the carbons are not bonded to each other. Okay? It has two carbon atoms and has a hydrogen group attached, or hydrogen atom attached to the ester functional group. Remember that the R group stands for an alkyl or acyl or an aromatic group. So it can be this CH3. Again, remember that carbons are not bonded to each other. Following this two carbon atoms, another simplest ester that we can find is the 3-carbon esters, and there are two types of 3-carbon esters. You can notice here that we have ethyl formate and methyl acetate. Okay? Our functional group again for esters is COOR. So for our first 3-carbon esters, which is ethyl formate, has an ethyl group replacing the R group. Right? This is our R group, or the rest of the molecule. And on this part, we only have a hydrogen attached to it. On the other hand, of the 3-carbon ester, we have methyl acetate, wherein we have a methyl on the R group, or the rest of the molecule. And in the other side, instead of a hydrogen attached to our central carbon, we have another methyl group. Right? So both of these are 3-carbon esters, but they are different types of molecule. Following these 3-carbon esters are our simplest aromatic ester, wherein it is derived from the structure of a benzoic acid. So again, instead of having a hydroxyl group, in this part, we are replacing the OH with an OR, wherein the R or the rest of the group is replaced by a methyl group. Hopefully, you understood the structure and the examples of the simplest ester. All you need to remember for esters is that they are derivatives of carboxylic acids and their functional group is COOR. Okay? Let's now move on with esterification. What is esterification? Esterification is the reaction of a carboxylic acid with an alcohol or phenol to produce an ester. So esterification is simply the preparation of esters. Okay, when esterification happens, we are producing an ester here using a carboxylic acid and an alcohol. Esterification requires a strong acid catalyst, such as sulfuric acid. Remember that when we say a catalyst, it speeds up the reaction of our chemicals, like the carboxylic acid and the alcohol. So this is what it would look like so that we can visualize esterification. Again, it's a carboxylic. Remember that carboxylic acid is R attached to COOH. Okay, we have a carbonyl here and a hydroxyl. Reacting it with an alcohol, which is an ROH, with the acid catalyst, it will produce ester and water as its byproduct. Let's take a closer look. Again, water is the byproduct of esterification. So we have here a carboxylic acid reacting with an alcohol, or it can also be a phenol. And then we have a strong acid to catalyze or to speed up the reaction to produce an ester and water. Okay? You might be thinking that the bond that is being broken in the carboxylic acid is the hydrogen only and it bonds with the OH in the alcohol, but that is not the case here. What happens here is that the hydroxyl breaks apart from the carboxylic acid, and then in alcohol, what breaks apart here is our R group and the oxygen, leaving the hydrogen alone. Again, there is a substitution reaction that happens here. So OH from the carboxylic acid will be substituting with the R group and the oxygen from the alcohol, which will result to an ester and a water byproduct. As you can see, OH here will combine or will bond with the remaining hydrogen to produce water, and the OR group from the alcohol will bond with the remaining carboxylic acid to produce ester. Now that we know what esterification is and how esters are being formed, let's proceed with nomenclature or the naming of esters. For the naming of esters, we have to visualize them as having an alcohol part and an acid part. Okay? We have to remember which is the one from the carboxylic acid, and we have to remember what is the alcohol used in producing this ester. So first step, the name of the alcohol part of the ester appears first and followed by another word for the name of the acid part of the ester. So there should be a separation between the alcohol part and the acid part of the ester. The name of the alcohol part is the R group bonded to O, or the alkyl group, or the OR portion of the ester. Later on, we'll see some examples and exercises for us to familiarize ourselves with these rules. The acid part, on the other hand, is obtained by dropping the ic acid in the name of the carboxylic acid and changing it to ate or ATE. Let's take a closer look at our rules for the IUPAC nomenclature of esters. Our first rule for naming esters is that the name of the alcohol part of the ester appears first, followed by another word for the name of the acid part. We have a note a while ago that we have to separate the acid part and the alcohol part in terms of naming esters. We have a given example of a chemical equation below, or a chemical reaction of esterification. So we have here our carboxylic acid, we have our alcohol, which produces ester and water. So this is our carboxylic acid, our alcohol. This is the product, which is ester, and the byproduct, which is water. So let's name them first. So this one is an ethanoic acid. It has two carbons. So this is an ethanoic acid. And since in carboxylic acids, we've discussed it in the last video, that we usually use the common name for the carboxylic acid. So ethanoic acid's common name is an acetic acid. So we will be using this name, acetic acid. For the alcohol, on the other hand, this is two carbons, so this is an ethanol. So how do we name them? First, you identify which is the alcohol part and which is the acid part of the ester. So the name of the alcohol part is the R group. For ester, we have to remember that our functional group is COOR. For this one, the R group is an ethyl. We have two carbons here, so this is our alcohol part. This is from the ethanol. So we have ethyl. And then for the acid part, it is obtained by dropping the ic acid ending of the parent carboxylic acid and changing it to 8. So again, as I've mentioned a while ago, we will be using the common name for the carboxylic acid. And then, as said here, drop the ic acid. So we will be removing ic acid. What remains is simply acet. And then replace it by 8. Okay, let's add it, ATE. So this is now the name for our ester, which is ethyl acetate. Okay, again, let's go back to our rules. First, again, you have to separate the alcohol and the acid part. So how do you do that? First, you identify which is the alcohol part, and that is the R group bonded to the O. Okay, so in here we have ethyl. And then for the acid part, you just simply have to drop the ic acid. Okay, so we have here an ethanoic acid, or the common name. Usually common names are what we use for the carboxylic acid. So instead of acetic acid, we will change it to acetate. Combining the two, it will now be ethyl acetate. Hopefully you're following through. Let's try some exercises and naming esters. Again, prepare a scratch paper so that you can follow through with our naming. Let's try to answer this now. Instead of giving you the whole chemical reaction with the reactants being shown a while ago, let's try to answer this ester only. Again, first we'll have to separate the alcohol part and the acid part. So the alcohol part is the one bonded to O. So this is the oxygen that we are referring to. We will have to identify the alcohol part attached to it. So we have 1, 2 carbons attached to it, or so 2 alkyl groups. So this is an ethyl. And then for the acid part, we simply have to count or to look at the carbons attached to the other side of the O. So we have this one. You have to look at the carbon side. So meaning you have to look for the double bonded O and then start counting from the carbon double bonded to O. So we have here 1, 2, and 3. Okay, so we have 3 carbon for the acid part. So we have here propane, which means that the carbon or the acid used for esterification is a propanoic acid. And as per our rules a while ago, we have to drop the ic acid and change it to 8. So this will now be ethyl propanoate. Let's check if our answer is correct. And yes, this compound is named ethyl propanoate. Let's try another example. Again, for this compound, we will have to identify which is the alcohol group and which is the acid group. For the alcohol groups, we have to look for the alkyls attached to our oxygen. So here is the oxygen that we are talking about, and we have here one alkyl group attached to it. So we have methyl. And then on the other side, we have here 1, 2, 3, 4, and then we have a substituent, which is another carbon alkyl group. So we have here 1, 2, 3, 4, we have butane. And then since it's we're first referring to the acid, it's butanoic acid. And then we have a substituent here, which is located on carbon 3, and it's a methyl group. So this is 3-methyl butanoic acid. We're not stopping here. We have to change the ic acid to 8. So this is now 3-methyl butanoate. Right? So you might be asking, how are we going to place the alcohol group to the acid group? You have to place it in front of our acid group. So our final name for this compound will be methyl 3-methyl butanoate. Okay? Again, there is a separate word for the acid part and the alcohol part. And alcohol part should appear first. Again, this is methyl 3-methyl butanoate. Hopefully, you've understood the naming for esters, and that would be the last part of the discussion about esters. Next, we'll be discussing about the physical properties and reactions of both the carboxylic acids and esters. You might want to take a quick break and then go back with our discussion. Let's now proceed with the discussion of the physical properties and reactions of both carboxylic acids and esters. Let's take a look back at our outline that we've shown at the beginning of the part 1 of Module 8. For this last part, for the physical properties and reactions, we're going to be talking about both carboxylic acids and esters. And in addition, for carboxylic acids, we'll also be discussing carboxylic acid salts and its uses. For esters, on the other hand, we'll be discussing ester hydrolysis and saponification as part of the discussion of reactions involving esters. Let's start our discussion with carboxylic acid, with its physical properties. First is its behavior at room temperature and at normal pressure. Straight-chain carboxylic acids with 1 to 9 carbon atoms are liquids and strong odors, while straight-chain carboxylic acids with more than 10 carbon atoms are waxy solids and with no odors. This means that with the increasing carbon atoms, the behavior of carboxylic acids is different, considering that they are at room temperature and at normal pressure. When we say straight-chain carboxylic acids with 1 to 9 carbon atoms, these are also known as low molecular weight carboxylic acids. Again, they behave liquid at room temperature and pressure, and they also have strong, distinct odors. While as they increase for more than 10 carbon atoms, carboxylic acids with high molecular weight are waxy solids with no odor noticeable. In terms of their melting and boiling points, we have to remember that carboxylic acids are considered as the most polar organic compound. This is because of the presence of polar carbonyl group and the polar hydroxyl group. Because of these two functional groups present in the carboxylic acid, this makes the carboxylic acid the most polar organic compound. Another thing that affects the melting and boiling points of the carboxylic acid is their ability to readily form hydrogen bonding because of their strong polar groups. They can readily bond with other or with themselves because of this free hydrogen that they have. Because of this, carboxylic acids are considered to have the highest melting and boiling points in comparison to the other types of organic compounds. These are some of the notable physical properties of carboxylic acids. Let's now proceed with the carboxylic acid salts. This is involving the chemical reactions that we can observe in carboxylic acids. Similar with inorganic acids, carboxylic acids, even though they are considered as weak acids, react with strong bases to produce water and carboxylic acid salt. This process is also known as neutralization, wherein we combine acid and base to produce a salt and water. Carboxylic acid salt is an ionic compound wherein the negative ion is a carboxylate ion. So what happens when you mix strong base with a carboxylic acid is that the hydrogen in the hydroxyl group of the carboxylic acid breaks its bond and then it produces a carboxylate ion. Again, remember that this is the negative ion. Okay? The carboxylic acid will produce a carboxylate ion, which is our negative ion. Let's take a closer look at some examples. Here is an example of a strong acid interacting or reacting with a carboxylic acid. And as you can see, it formed a carboxylic acid salt. This is the salt and the byproduct, which is water. So we have here the carboxylic acid or the COOH. We have here our strong base. So what happens during the formation of the carboxylic acid salt is that the hydrogen, as mentioned a while ago in our carboxylic acid, breaks its bond. And then in the strong base, the hydroxyl breaks its bond from the element. And then a substitution reaction occurs. Okay? The hydrogen and our positive, this is now considered as the positive ion, substitutes their places. So what happens is that hydrogen bonds now with the hydroxyl group to form water. And then our positive ion bonds with our carboxylate. This is our carboxylate ion. Again, this is the negative ion. Bonds with the positive ion to form a carboxylic acid salt. Let's take a look at the rules on how we name carboxylic acid salts. Naming COOH salts or carboxylic acid salts is similar to naming other ionic compounds, wherein the positive ion is named first, followed by a separate word for the negative ion. We have to remember that the negative ion here is our carboxylate ion, which is this one, and our positive ion is from the base that we use. So this is our positive ion. So let's take a look at our equation. In this equation, we used formic acid, which is the common name for the methanoic acid, combined it or reacting it with a strong base, which is a sodium hydroxide, to produce water and sodium formate. Again, the positive ion is named first, which is our sodium, followed by the negative ion, which is the carboxylate ion, which is formate. Now, why is it formate and why did we not use formic acid? Keep in mind that carboxylate ions are named by replacing the ic acid ending of the parent acid and replacing it with ate. So instead of formic acid, we have to replace ic acid. So you now have only form, replacing it with ate. So it will be formate, indicating that this acid is now a carboxylate ion. That's why our salt product is now named sodium formate. Now let's try to have this exercise wherein we will be writing the chemical equation for the given carboxylic acid salt. In the past exercises, we are identifying the product. We are naming the product of the reaction. In this one, we will be identifying what are the possible reactants that produce this carboxylic acid salt. For the first one, let's try to look for the possible reactants that produce sodium propionate. This is the structure of sodium propionate. Again, the positive ion here as shown in our structure is the sodium, and our negative, of course, is our carboxylate ion, which is our propionate. To identify which acid and which base is used in this one, first, the easiest way for you to identify is to look for the acid. Right? And how do you look for the acid? You just simply have to revert it back to the acid form. Okay? The carboxylate ion, you revert it back to its acid form. How? Simply remove 8 at the end. So it's propion. And then change it with the ic acid. Simply add ic acid. You now have identified, okay, you now have identified which acid is used in our reactants, which is propionic acid. For the base, on the other hand, you simply need to add a hydroxyl group in our positive ion. So you now have Na for the positive ion, which is sodium, and simply add a hydroxyl. Okay, this is now your strong base, sodium hydroxide. Let's take a look if our answers are correct. So we have here propanoic acid, which is our IUPAC name, because propionoic acid is our common name. As I've said in the past discussions, we usually use common names in naming carboxylic acids. So its IUPAC name is propanoic, and then the base that we use is sodium hydroxide to produce sodium propionate and water. Right? Hopefully you got our exercise. Let's try another one. For the next one, we have potassium acetate. Here is the structure for our potassium acetate. Our positive ion here is potassium, and our negative ion or the carboxylate ion is acetate. Again, similar to what we did a while ago, in order to look out or in order to figure out which acid is used, simply change back the suffix ate to ic acid. So this is now acetic acid. And then to look for the strong acid that was used in the reaction, you have to look for the positive ion, which is potassium or K, and then simply add back the hydroxyl group. So we now have our potassium hydroxide. Let's check our equation if our given reactants are correct. So we have here acetic acid combined with potassium hydroxide will produce potassium acetate and water. So as you can see, we have correct answers for the reactants. Now you can revert back this formation of carboxylic acid salts back to their parent carboxylic acid. How? Simply react the salt with a strong acid to convert a carboxylic acid salt back to its parent or to its original carboxylic acid. The strong acid that we are referring here that can convert the salt back to carboxylic acid can either be hydrochloric acid or sulfuric acid. And then as you can see here, this is our salt. Simply react it with a strong acid, given here is HCl, and it will produce the original or the parent carboxylic acid and another salt. So you can revert it back or you can reverse back the reaction. Let's take a look at this diagram to visualize this interchanging of our equation or our reaction. Okay. So the interconversion of carboxylic acid salts and their parent carboxylic acid is easy and is considered interchangeable. As you can see in our diagram, if you have a carboxylic acid, you simply add a strong base. So it can be in form of an NaOH or potassium hydroxide. And then it will produce a carboxylic acid salt. Now, if you have a carboxylic acid salt and you want to revert it back or you want to bring out the parent acid or the parent carboxylic acid, you simply need to react it with a strong acid, which is HCl or a sulfuric acid. Okay, so it's interconversion or interchangeable. Now that we've discussed how carboxylic acid salts are produced or how the reaction happens, let's take a look at what are the uses of carboxylic acid salts and why are they important. There are various uses of carboxylic acid salts. First, it enhances the solubility of medication. Right? Carboxylic acid salts are soluble, that's why they are added to medicines to enhance the absorption and the solubility of the medication that is given. Some examples of carboxylic acid salts are benzoate salts, which are effective against yeast and molds in beverages, jams, and jellies. Another example are sorbates, which inhibit mold and yeast in dairy products, dried fruits, and some meat and fish products. Okay? They inhibit the growth of mold and yeast. Another example is propionate, used in the preservation of baked goods. Please keep in mind that benzoate and sorbates can be used in yeast-leavened baked goods as they inhibit mold and yeast. Okay? So benzoate salts and sorbate salts cannot be used in baking, especially those that needs rising of the yeast or rising of the dough, because as their job is to inhibit, okay, the growth of mold and yeast. You also have to keep in mind that COOH salts or carboxylic acid salts do not kill yeast and molds. Okay, what they do is that they only inhibit the surrounding or the environment. They make the environment not suitable for yeast and mold to grow. We're now done with discussing the physical properties of carboxylic acids, the reaction of carboxylic acid salts, and its uses. Let's now proceed with the esters and its physical properties. Esters have no hydrogen atom attached to oxygen atoms. Therefore, they do not form hydrogen bonding among other molecules of itself. So they are the opposite of carboxylic acids, which readily bond because of the hydrogen. Because of this, they have significantly lower boiling point than alcohols and acids. Keep in mind that low molecular weight esters are soluble in water because they can form hydrogen bonding with water molecules. This hydrogen bonding with molecules, considering that they are only low molecular weight. If the ester has 5 or more carbon atoms, they are sparingly soluble in water or they are slightly soluble with water. They are already having struggles being dissolved in water. Right? So similar again with carboxylic acid, as the carbon increases, okay, their solubility in water is affected. One significant property that can be observed in esters is that they have a pleasant odor. Okay? This is the opposite of the carboxylic acid, which can either have an unpleasant or strong odor and no odor. Esters, on the other hand, one notable property on here is that they have a pleasant odor. Sometimes this is observable in flowers and in fruits. Let's now take a look at some of the chemical reactions involved in esters. First is ester hydrolysis. When you say hydrolysis, it's simply adding water to a compound. So in ester hydrolysis, this is breaking the carbon-oxygen single bond that holds the alcohol part and the acid part in the ester. So what happens here is that ester reacts with water to produce carboxylic acid and alcohol. As you can see here, you have an ester combined with water, and then it produces a carboxylic acid and an alcohol. So what happens here is that there is a breaking in the bond between the carbon and the oxygen that separates the alcohol part and the acid part. If you remember in the naming of esters that we've discussed a while ago, there is a separate alcohol part and acid part in an ester. So during ester hydrolysis, we break this bond and then we produce carboxylic acid and an alcohol. So as you can see here, the hydroxyl group from water will bind with the ester, replacing the OR group to produce a carboxylic acid. And then the remaining hydrogen here will bond with our OR from the ester to produce an alcohol. Ester hydrolysis needs a strong catalyst such as an acid, a base, or an enzyme. So we need a strong catalyst to fasten up or to speed up our reaction. And then as you can see here, this H+, this is our catalyst. It can be again an acid, a base, or an enzyme. So again, ester hydrolysis results in the formation of an alcohol and a carboxylic acid. So you might notice it by now. If we are to compare ester hydrolysis and esterification, they are opposite reactions that can either produce carboxylic acid and alcohol or an ester with the help of this strong catalyst. We've discussed earlier during the discussion of esters, the esterification wherein we produce esters by combining carboxylic acid and alcohol. Ester hydrolysis is the opposite. We are producing carboxylic acid and alcohol by simply adding water to esters. You might be familiar with this diagram. This is also the same diagram or similar diagram during the carboxylic acid salts. This means that you can interchange esters and carboxylic acids as long as you have the strong catalyst. So you can form ester from carboxylic acid and alcohol, and quite the opposite. You can form carboxylic acid and alcohol from esters. Okay, in ester hydrolysis, you simply add here water plus the help of a strong catalyst. Let's now proceed with another chemical reaction involving esters, which is saponification. Specifically, ester saponification. Saponification is the hydrolysis of an organic compound in which a carboxylic acid salt is one of its products. It can happen to esters, amides, fats, and oils, but for this part, we will only be focusing on ester saponification. So as you can see here, you have an ester combined with water with the help of a strong base, and then you will produce a carboxylate and an alcohol. This is not similar to ester hydrolysis because you might be confused. In ester hydrolysis, we are combining ester with water with the help of strong acids or enzymes to produce carboxylic acid and alcohol. In this part, we have ester, water, and strong base to produce a carboxylate, which is a carboxylic acid salt, and an alcohol. Sodium hydroxide or potassium hydroxide is usually used as a base in ester saponification to produce carboxylic acid salt and alcohol. Again, carboxylate, combining it with a base, will produce a carboxylic acid salt. We are now done with discussing Module 8, Part 1, wherein we've discussed carboxylic acids, esters, and their physical properties and reactions involving them. Hopefully, you are very familiar, especially with the naming of our compounds. After watching this video, Kindly answer the practice tests that will become available for you to be able to identify if you really understood our topic. Keep in mind that this practice test is not recorded and it will serve as a review and a practice for you to be able to understand if you really followed through with our discussion. If you have any concerns or questions regarding our discussion for the part 1 of Module 8, kindly do not hesitate to reach out to me through Canvas inbox or through my email. Thank you and God bless.